My name is Frederick, and this is my second IP hand-in with 45 filters. Excuse my voice, I have had the flu for the last week and a half, so might not be the best voice. So let's take a look at the filters. I did invert, simple brightness, contrast, auto contrast, lock, X, gamma correction, salt and pepper, alpha. Yeah, just all those here. I'll start by going through some of the interesting ones, and then look at the code that we use for all of them, and then some of the specific code. If you, for example, take a look at the first one, invert, then we always start up by making a width and a height variable. Then we want a texture which will hold our finished image, and then we'll have a video grabber which will grab our image from our camera, webcam, and then we'll have an unsigned char pointer which will be called output, and that holds the array that we store our pixels in after they have been processed. We always declare our width and height, and we do this up here, or we have this size here because if the width, let's see, if width is 320 and height is 240, then our image will contain 76,008, I think 800 pixels. Let me check. Yeah, but this is for a grayscale image. If we have an RGB image and color image, which we normally have, then we have three channels. We have the red channel, the green channel, and the blue channel. Those are three extra channels, so we'll have this, we'll multiply it by 3. So now we will have 230,400 pixels instead. And that's a lot of pixels to go through. And if we just multiply it with 2 here, we'll almost get 3 times as much. So therefore we will just stick with this small image here, and it will be fine. We can still look at it and it's still pretty. And next we take our video grabber and we set verbose to true. We take our video grabber and we initialize the grabber and grab the frame with the width and a height that we want. We defined up top up here. Then we take our output, set it to a new unsigned char array, and then we take the length of the array is the length of all our pixels in a color image. Then we take our video texture and allocate it with width and height and the color scheme. We take the background, set it to black, take a video and we grab the frame. Then we check if we have grabbed a new frame. And if we have that, then we take this is if we are doing the same thing for all our pixels. That means for all our channels too. We just make an integer that's as big as all our pixels combined. Then we grab our pixel and we call that char pixel, and then we run a for loop 230,400 times, and we just take our output array and that's set that equal to 255 minus the pixels value, which is just a single for loop. That's one way of doing some point processing. And then now we take our video texture and we load our data into it, and that data is our output, which is our kind of new texture, but that's our array with all our pixels stored in. We set the width and the height and the color scheme. And we set the color to 255, draw our original frame, and we draw our new texture. And that texture we draw at width in and 0 and width height. So if the first image is 0.0 up here, then the next one is at width 0.0 here, so they're lying next to each other. It's basically the same of writing 220, no, 320 0. So let's take a look at this here, and this is just simple inverting. As we can see here, inverts the picture, pretty standard. We can do this because we know that if we have a color, for example this green one here, and we want the inverted color of that, just minus with the minus with 255, and then you get the correct one, and the correct inversion looks like this. So it's pretty easy. So that was the first one. It's pretty simple to do, and that's a simple standard one for loop. Let's take a look at one of the other ones. We can take a simple brightness, for example. It's a bit different, but not a whole lot different. We still just have one for loop. Instead of taking minus, what can we say here? In the first one we take 200. Oh, that's I want another color. To 255 minus the color, and we got the inverted. Now to get the brightness, we'll take the color and plus with brightness. And we get, new image, new bright image. So it's pretty simple. Take a new pixel and set it to pixel plus brightness, and if the pixel exceeds 255, it will just be 255, and if it's less than 0, it will just be 0, and I'll just take that as a new pixel. So as we can see here, I can use my up keys to make the image brighter, and then I can use my down keys to make it darker. And as we can see down in the output log, I don't know why it does not go less than 0. I'll try again. See if we can get it really dark. There we go. See? So it's pretty easy. I use a switch statement for our OF key up and OF key down to change the brightness, and then I just see it out. I made this in different files for faster compile time and for easier way of looking at it. It could have been done in one single file. You could easily have just made like a new integer and call it like num, and then down here we could just say like say case a, for example, and then we say num plus plus, and then for example case a d will be num minus minus. No, that's not num. And then we'll just have a num equal to 0. So it starts on 0, and we can actually do up here, we can say if num equal to 0, then we will have this texture here. So this is what will happen if num is equal to 0, but we can then have a new one saying num equal to 1, and then we can have like, well, we could have the exact same thing, but we could have another filter here, and you could just use A and D to change between the filters, but that takes compile time, and it's not really needed. It's easy done, but it's much simpler to have them in each different one here. So let's take a look at the contrast. The contrast used a bit different setup. We still use color images, but we use two double for loop, or a double for loop. So instead of let's just move it up here. I'll move it over here. We can use it later. So instead of just having one for loop, that where we take each pixel and that's RG and V pixels for grayscale. Now we have two double for loops, so that means that the first double for loop we will goes from Y until width, no, until height, sorry, and the next double for loop goes from X until width. So it's just another way of doing it, and this is more or less if we want a specific point in the image, or we want to just run it through it differently. And for some of them I chose the simple one for loop, some I choose two for loops, for even more I choose three for loops because you need one for each color. For example, in the double for loop, if you want a specific pixel, you don't care about what color it is, you just use pixel and then Y times W plus X. Just get a pixel out here. But sometimes we need three for loops because we have one for loop from C until 2, or 0 until 2, which gives us our colors for RG and B. So if we want an R, it's pixels. Then we have Y times W plus X plus 3 times C. Oh, that's not a C. That's not a C. Plus C. Now the first one, oh, yeah, for color. C, if C is equal to 0, then we will have green, and if C is equal to 1, then we'll have no, C is equal to 0, that's red. Then it's green, and then if C is equal to 2, we'll have our blue color channel. That's pretty easy too. So for the contrast, I take two for loops. Oh, they go from 0 until height and from 0 until width. This is just one way I tried to do the contrast. Didn't work correctly, so try another one. I have my red pixel. That's just as I explained. Yeah, Y times W plus X times 3 plus 0 plus 1 plus 2. Then I have a switch case that goes 10 up or 10 down each time, and it cannot go above 100 or below minus 100. That contrast, I use the formula called 100 times plus that contrast value divided with 100 is equal to my new contrast value. That new contrast value is multiplied with contrast values. So it's a formula from, let's see here, from this image processing here. Take a look at our contrast formula here. Yep, this is how we do it, and then this is for each pixel. So that way we can take our pixel R. I just set it to 0 in the beginning, so I'm sure there's not something wrong with it, because it's a double. I did not define it above, so just to make sure it's not holding some random weird number. Just set it to 0. Then I take pixel R and I put it equal to R divided with 255. Then I minus with 0.5. Then I multiply with the contrast value. Then I plus with 0.5, and then I multiply it with 255. And then before I set my output value to that pixel value, I make sure that it's not less than 100 or not above 255, because then I'm sure that it's in our spectrum. And I do the same with the G and with the B. So if we take a look here, we'll see we have a normal picture. We can make it darker in contrast, and we can make it lighter in contrast. So the darker works really, really nice. It's easy to see. The lighter is a bit weird, but I guess that's the way it works. And we can see down here, if we have our contrast value at 1, then our N contrast at 0. Now it's at 10, 20, 30. Then we get our contrast value up a bit, and we can see our RGB values over here. And they quickly go down to 0 when it gets too dark. The alpha and beta is just from an old test, so nothing to worry about. Okay, and I just made the string using a string and a off-draw bitmap string standard. So that was that's a contrast. Auto contrast. I made some switch state or some if statements just to check what color is. If the colors, I make the lighter colors lighter and the darker colors darker, so it gets kind of auto fixed. Might not look correct, but I'm not really sure how an auto contrast should look. So I made the darker one darker and the lighter one lighter. The lock and the X filter, they are really simple. It's almost the exact same as the invert. Let's just erase some of this here. Yeah. Okay. So if we have our what here from before. Now to get our lock filter, we take so we say lock that's equal to just the lock value of our color. That's really simple, but the log value of our color is low, so to get it up higher we multiply by 30. And I tested out a few values. 30 seemed good, so I just use 30. But the problem is that when we use lock, we need to use a double. We cannot just use an unsigned char as our pixels. So I could typecast it. I actually made a new value called pixel D, pixel double, and just set that equal to the pixel value. Just to make 100% sure, I have had problems with typecasting, so this is just an easy way. And if we take a look at the filter, we can see that this is a log value. Looks pretty fun. And the X value, pretty much the same. It also requires a double, but here we don't actually need to multiply by anything. So I can just cast the filter, and it looks like this. No idea if it's correct, but it looks fun. It looks strange. Okay, so let's take gamma correction. Let's also take that one. So this is one way I found out I could use the gamma correction. I'm not 100% sure if it's correct. This is 0.1 each time I press up and down. Not a lot, but it should work. Here I typecast our Untitled Chapter as double and my gamma. I don't know if actually why I typecast that. Oh, it's a float. I could just use double, but I use a float. Never mind. And I used in the power off to get the gamma. Okay, let's look at some fun ones, because this will take a lot of time to go through all of them. Actually, not a lot. I'll take the salt and pepper. Let's just continue. Okay, so what we do here is that I make the image black and white, or grayscale, and then I add a salt and pepper noise. So what I do is I add 10% salt and pepper noise, and I do this by taking 2 for loops here, as we used before. Then now I want to make a grayscale image, so I take my pixel, my green, my blue, my red pixel, plus them together, divide them with 3. Now I have my output pixel. So I actually take, if we have, we can erase this now. Okay. So if we normally have our image here, and then we have like, this is our red, this is our green, this is our blue image above here. So if we take the first pixel here, and here, and here, now I plus them together. So we will have, for example, if we take, let's just take this, take this color here. This is our color for our complete image. This is our green color. This is our red, this is our green. This is our blue. If I multiply those together and then take like the grayscale value of that, if you can say that, then I'll get a grayscale value. I will just plus those together, because that's from up here, and I will just get 1 image and not 3 behind. So I do that, and then I take a random number between 0 and 100. Then I check if that number is less than 10, so that's 10% of the times. And then I take a new random number between 0 and 2. And if it's 0, then I make the pixel white. But if it's not 0, then I make it black. So if we look here, 10% of the time there's a noise, and 30% of those times it's white, and 60% of that time it's black. So that's a salt and pepper noise. Okay, let's take a look at the alpha blend here. So I was unsure what to alpha blend with, so I just choose the Lena image that we used multiple times before, and I use my arrow keys to blend. So I loaded my new image in, I resized it so it was the same width and height. Then I had an alpha of just an alpha float, put it to 0.0. And again I used a single for loop, and the way I got the alpha was to take the image pixel, multiply it with my alpha value, plus with my image pixels, multiply it with 1 minus my alpha value. My alpha value goes from 0.1 up until 1. So yeah, not much to say here. um, Alright, so let's take a look at. We almost covered RGB to grayscale. Actually, we did, but what we need to make. We need to. Yeah, so here you have a grayscale image. What I did was, instead of having, normally we have times 3, so we have 3 channels. We don't need that. Instead of using RGB or GL RGB, we use GL luminance. And the same down here, GL luminance. And as I explained before, we take all our 3 pixels, plus them together, divided by 3. So that's easy. So if we want it in binary, that's only black or white. There's nothing grayscale about that. We can take a look at this, for example. We again use luminance, but this time we have a simple if statement and saying that if our output is less than 100, then it's equal to 0. But if it's more than 100, it's equal to 255. Actually, I have an idea just to make some fun out of it. Let's take just make an int called num. Let's set that to 100. And let's set this to none. And then let's make a switch statement down here. T or T up. Let's say num plus plus. And then just C up. And then OF key down. Num minus minus. Now we can actually try and change the value to get more or less white on our image. So here we can see that our output goes up and we get less and less white on our image, and we can put it down and we get more and more white on the image. Actually, maybe like 95 is better. This is 95. This is 100. It seems there's a bit too much black over here. Set it down to 95. That's a bit better. We go down to like 90. It's too much white over here. But my eye here is weird. See, this is better. Yeah, I don't know, around 95, 90, 90, 95. But this is something you can check if you have the key presses, so that was just fun. Oh, this is a fun filter. Again, using standard double for loop. Yeah, just forget about this. This is not used. Okay, so I take my red pixel, set it equal to my red pixel, my green, set it equal to green, and blue equal to blue, standard. Then I make some doubles. I don't need them anywhere else, so I just define them in here. I should probably define them in H, but this is easy. So I take those doubles here, set them equal to R plus G plus B. So if I actually divide it with 3, I could kind of get a grayscale, but not really. And then I make some result R, result G, result B. Those are actually defined in the beginning in here as untitled chars. I take R divided with capital R and multiply it with 255. Because the formula for normalized RGB is, you can actually look that up in our book, and that's R divided with R plus G plus B times 255. That's pretty simple. And of course for the yeah, you get the picture. So let's take a look at how that looks. So this is Normalized Colors. Pretty ugly. Yeah, it can be used in some computer programming if you want to. If you have some sharp colors, for example, the red on my shirt, it's extremely sharp now. And it's, for example, have a half a red line on the ground, and your robot needs to find that red line. You can convert it into normalized, so it's extremely clear that it's a red line. And again, I just use a standard off-draw bitmap string to get the output here. Okay, so let's see here. Let's take a look at the. We can take a look at the next one here. It's really bad. Yeah, we want to convert it from RGB into hue, brightness, saturation, but I'm not really convinced that this is possible this way, since we actually have our RGB. We have our three images here, which is red, green, and blue. But I don't think that openFrameworks works kind of this way. If we take it and do hue, brightness, and saturation. Well, because we take the values from this pixel and we set it equal to this pixel here, and it looks weird. This formula is correct, but it looks weird. But okay, what I do is I tested this formula out in Photoshop just to see if it actually gave something that looks correct, and it did. So we take a look here and we say that the RGB pixel standard, we take typecast as a double, because it's an unsigned chart. If we divide with 255, we cannot do that, so we have to typecast it as a double. And then we take a new minimum of our G and B, and what we do is that we check. There's a minimum function built in, but I just did my own here because it's easier and I'm 100% sure what happens. So I check for the minimum value from G to B, and then I check the maximum value from G to B. It's just done here, this simple if statement. And then we take minimum value from RGB, and that's the minimum value of R versus the minimum value from the GB, because we cannot take the minimum value of R and G and B in the same time. So we take G and B, and then we take R. And then I check if our minimum RGB is equal to our max RGB. If it is, then our W, yeah, that's actually our brightness. Why did I call it W? I don't know. Or V. I don't know. And if it is, then we know that our output image has to be 0, 0, and then the V down here. That's just how it is. Else, if that's not correct, and in many cases that's not correct, then we take D, which is just a double, if I believe. Yeah, it's just a double. And we set that equal to, we set that to either G minus B or G minus R minus G or B minus R with an if statement. We do the same with H. We said that if R is equal to minus RGB, then we set HH to 3. If it's not, but if B is equal to minus RGB, we set it to 1, and else we set it to 5. And then we take our hue, and we set that to 60 times HH, which we found up here, minus with D, which we found up here, divided with max RGB minus minimum RGB. And then we set our sortation to max minus divided with max, and then V to max, and then we put that in our output image. But my doubt is that the same channels can be used for the same kind of values, and that's why it does not really look extremely good here. It's very, very red. Yeah. So I'm unsure if this is the correct way of doing it, but the formula is correct. Or maybe I actually, no, never mind. Yeah. So let's take a look at our ACos filter. That's very much the same as our log and X filter. I found a double for pixel D, pixel 1, pixel 2, and pixel ACos. Set pixel D equal to our pixel, so now we have our pixel value in here, and pixel 1 is equal to. The problem is that to take ACos of something, we need to have a low number. We cannot take it for example, 255. That just does not work. So I divide with 100, then I take ACos, and then I multiply with 100, so we get a higher number again. And when we do that, we will have a filter looking like this here. So that looks kind of inverted. My teeth looks really weird. Yeah. Maybe I have some color things here. Let's see. Yeah. So the white, you can say, gets all black, and some of these things here are inverted. So that's a fun filter. Let's see how far we are with time. Almost 40 minutes. I'll continue. So let's check out the color depth. Let's see here. Let's take a look at the filter. Oh yeah, and then I can use the arrow keys to change the color depth. Why does this happen? Let me check 1 second. You are. Oh yeah. Oh I know. I had some problems with my unsigned char, so I'll just cast this as a double. Hopefully it will fix it. Also, I'll take a look at it. Yeah. Okay. So here we can decrease the depth of the image or increase. So what we do here is that we increase in 8ths, and we use a formula called newr, which was before an unsigned char, but I made it a double, so we can check if it's larger or smaller than 0 to 55. So I'll take my newr and I plus it with the offset, which is just, well, in 8ths, divided with 2, minus my r plus my offset divided with 2, modulus my offset minus 1. And that's a formula we can use for changing the color depth. It works. It looks fun. Hue shift, rotation shift. Since George told us we were allowed to use the hue shift function in openFramework in OpenCV, it's almost too easy. So yeah, we can shift hue here. It's actually cool filter, because you can get a very green person, or a very blue one, or a pink one. And the same with saturation. I do it in intervals of 5. So we can see here, we can change the colors, and let's see if this is more colory like than my faces. So we can see, like, for example, the red one changed to gray, the blue one, it's still blue, the green one is still green. Now we have almost a grayscale image. Yeah. So Sepia is a fun folder. Okay. On house time. Well, it's a long assignment. It will be a long video. So this is my. This happens again. Ah, damn it. That's again my mistake of not using doubles, because doubles is the best. Oh, I'm not actually checking if it's outside the range. These are if R is less than 0, SR is equal to 0. G. Alright. And then if SR is more than 255, SR is equal to 255. Woohoo! Let's see here. See, now it looks better, because the white before, the white could go outside the range of 255, and then it would look weird, but now it cannot. And also the black could be darker than black. So how do we get these colors here? Well, we take R, multiply it with 0.393, plus it with G, multiply it with 0.769, and plus with B, multiply it with 189, and some different values for each 3 of them. But that gives us this nice yellowish, old school Western look on our image. And this is a very, very common filter. All cameras have it like built in. Let's take a look at the pastels. I don't really like the pastels here, because I don't really have colors. So yeah. See, nope. It looks weird, but what I do is that this I'm actually not using. Okay, I take my color, divide it with 2, and then plus it with 127, because if I want to get, for example, a random pastel color, what I do is that I take a random number between 1 and or 0, 128, and then I plus with 227, because then I will get a light color. Here I just take my regular color, divided by 2, plus with 127, so I get lighter colors. It does not look good on this picture here. I could also have done a lot of if sentences to check if each color is in a certain range, and then I could manually figure out which range was best for them. But I did this, and then again I use these if statements here just to make sure that it's inside the scope. Oh, color detection pink. I like this one here. It took me longer time to find something pink in my room than it took to actually make this filler. So, well, what I do is that I have our double for loop here, have my colors, and I take result R, could be just result, but this is just a variable I copy pasted. So I say that if R is more than B minus 20 and R is more than G plus 90, then it's equal to 255, else is equal to 0. And then I set my output value for all my 3 colors to that color. So if we take a look here, and see here, we have just the pink and maybe a bit of my fingers because they are kind of pink. So this is how pink color detection works. Let's see here, that's actually my business cards, but it's just a pink. And that's really cool. And it took some time to figure out exactly what color pink is. See, my red is also kind of detect more than just pink. Well, it does detect pink, so I guess that's a pass. Green, you could just say like just the green color, but pink is a mix of more than just one color, so it took some time. Okay, let's go over to some kernels. The next couple of ones are like kind of the same, all of them. 3, 3, 7, 7, 7, 7, all the same. I have a kernel, 1, 1, 1, 1, 1, 1, 4, 1, and I divided with 9 because 1 multiplied with 9 is 9. And I run the kernel and set it equal to our kernel float value from over here. I do it from 0 to 2, 0 to 2, so I'll get all the values in. Then I make 5 for loops here. The first 2 go from 1 till height minus 1, and the next one from 1 till width minus 1. And this is done. Let me just erase some of this here. Because if we have an image here, and if our kernel lies, for example, if it lies here, say we have our kernel, this is our pixel, and our kernel will be from here to here to here to here, and this will be no problem. We can multiply all these pixels together with no problems. We can plus them together with no problems. But if our kernel lies here, now we have a problem, because then we would need something that goes out here, down here. That's no problem. This one here, this is no problem. This is no problem, but this is a problem. This is also a problem. This is a big problem. So these up here, there's no values in them, so we go out of bounds. So therefore we start, this is the first pixel we can use. This one here, because then we can use these other 8. Then we go through all our colors from 0 to 3, as explained in the beginning. And then we go through our kernel from -1 till 1, because we want to start here, so we go from -1 till 1, and from -1 till 1. And we take our output and we plus it with our pixels multiplied with our kernel, and we do this 9 times. And then our image will look a bit blurred. As you can see here, it's blurred. It's easier to see up here with my hair. It's blurred. So that's just a kernel. Exact same thing with 7.7. The difference between a disk and the mean 7 times 7 should be a disk. So what we're doing here is we are taking 0, 0, 0, 0, 0, 0. So where the other one was a square, this one is more round inside. So these we are not really using. It's this in here where we have our values. So that's called a disk because it's round like a disk. And 7 times 7, exact same thing as 3 times 3. Gaussian Edge, that's just another kernel. Sobel, another kernel. Oh, Sobel, we actually use 2 kernels. We have 2 kernels here. We don't divide with anything because 1 minus 1 plus 1 minus 2 plus 2 minus 1 plus 1, that's equal to 0. So we can divide by 0, but what's the point? So we take the 2 kernels, first run through one of them, then the next one, and then it looks weird. See here. So this looks bad because we have all the colors, but the contour of it is correct. But the colors need to be gone. This does not work by doing it at grayscale, so I'm not really sure why. My computer has some problems doing the kernels, so I'm not really sure. Create the same median. That's a way of, let's see here, I never remember all of those here. Oh yeah, we take the median value of our 9 combined values. It's lagging because it has to do so much at the same time, but that's also kind of blurred. What I do here is that I make it grayscale, then I go take my one for loop, then I make a vector of unsigned chars, then I take my kernels, or I don't have a kernel but I want to run from -1 till 1 anyway, and then I push that into my kernel, and then I sort my values inside the kernel, so from lowest to highest, and then I take the median value, since I know I have 9 because there's like 9 pixels. 1, 2, 3, 4, 5, 6, 7, 8, 9. Woohoo! So take number 4 because we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 8. So this one is kind of the middle. So that's the medium filters that I take the middle pixel and set that value. So that's what I do. The max is just taking the max. So instead of taking like so instead of taking the middle value, I take value 8 because that's max value, and it's even more blurred and weird looking, and it's really laggy because it has to do this, as we remembered before, a lot of times. Let's take a look at the minimum. Let's just take the minimum value. Actually, on this, I can use my arrow keys to change. So you can see it becomes more and more like normal, and then it becomes weirder and weirder again. Yeah. Let's take a look at the Emboss. Oh yeah, here I use my Emboss kernel. It's any other kernel, and you can see you have this is noise, it's just noise there, but you could see the contour and the emboss in the picture. And let's see here, what else do we have? This is again just some kernels I used. Let's go to dilation. Oh, it's almost an hour. Oh well. Okay, so okay. So we can see that first we have our original image, then we have bitmap, and then we have the dilation of the bitmap. And dilation is to take the image and make it, how can you say, if there's just one white pixel, you make it more white. So what I do is I plus together the pixels and check if it's more than one. Then I put them all to 255. And erosion is kind of the opposite. They need to be, let's see here. There needs to be exactly 9 pixels. If there's just one pixel missing, then we'll not do it. So you can see here we have, for example, my eye. There's not, we don't have 9 pixels here, so it removes automatically. And then we can combine those two inside an opening. And this is a combination of first erosion, then dilation. And that's kind of how you can open things up. So we have first erosion, then dilation, and then a combination of them. Yeah. And closing is first dilation, then erosion. Looks a bit different, but it's the exact same thing. Just making grayscale, making bitmap, making dilation, making erosion. Let's see what time. So we have a resize here. Use a resize formula here to make it stretching. As you can see here, the image is stretched. And let's see what we else have. We have a crop. Yeah, so it's cropped. And then Pixelate. So what it does is I replace the neighborhood pixel with like one more pixel. So it's kind of pixelated. I'll explain that further in the next one here, Pointinize. This is one of my favorite ones. So let's first take a look at the filter. So it looks pretty standard. And then I can use my arrow keys to make it more and more pixelated until we get to like this here, and this looks cool. This is a really, really cool filter. I like this one. And it was one of those where I couldn't find anything at all on the internet or in the book about it. So I just thought, well, I need to replace the neighborhood pixels, so let's just do this, and we can. This can go far up. There's that's funny. There's some errors down here. That's nothing is perfect. So what I'm doing is that I have my pixel size key up, key down, and I go until height minus pixel size, and so I say that I take my pixel size here. Wow, made these before Christmas. This is hard to remember. So I take a pixel, I take that color, and then I tell it in the output that the pixel plus the pixel size is equal to that color. So I take the first color, and then I say all the next pixels in the double for loop here will be that color. So I can draw like a square of that color. In Ribble, this is some sinus and cosine to make some ripple effects. Let's see here. So that's a way you can do some ripple effect. There's some errors down here that I tried to correct, but I couldn't really do it. So what I'm doing is I make a like a wave, and I take sinus to 2 times pi, or close to pi, times the float value of y divided with 128. And then I say, okay, so my new x is my x plus xo, and my new y is y plus xy. Then I check if it's less than 0 or more than width, because I need them to stay in bound. The same down here. And then I say my output pixel is equal to these things here, and else my output pixel is not equal to these things. So I just give them new values. Then tile, let's see what we did here. So I tried to do some tiling here, and it kind of worked for the first 3 ones, but then it kind of stopped. But I have 3 tiles, so that's kind of tiled. What I did was I tried to make some new height and new width, and then put the pixel into those new height and width, so I can draw them multiple times. And then let's see here, accumulate. What does that even mean? Oh, let's see how the filter is. I think that's just like plus 2 images together. No, that's just really fucking blurred. Oh, that's very strange. Let's see what I did here. So I have the pixel, I plus the pixels together and divide it. Oh, that's like an average of each pixel. So I'm trying to take the average of 5 pixels and put those on the pixel values. And I guess it kind of works since it's very blurred here. And then a Rhythmic Substract. Oh, this one was when you subtracted 2 images from each other. So I'm gonna take my linear image, and I take just a single for loop, and I take my output is equal to my image minus the pixel. Yeah, and then I check if it's below or above 255. I might try and fix this if it's not really working. Yeah, see here, okay, so it's kind of working, but I don't want these weird colors, so let me just try and see if I can fix that. I can fix it down here. Double mu output is equal to image I minus pixels I. Output I is equal to mu output. But I'm to check if your output is more than this, because then your output should not be the same here. So let's see. See, this works much better. So this is actually plus or subtracted from each other. It looks like I'm kind of behind her. I don't know if that actually fixes if you change position of these two here. Nope, that's just what you subtract from what. Kind of like this one better because it's lighter. So it's a fun thing. Let's see what happens if you actually multiply or add them together. That's a lot of light. Subtract is probably better. Let's just keep it on subtract. So that's also a fun image if you want to combine a few things. So that was 45 filters. Woohoo! That's an hour and 6 minutes. That's gonna be long. Well, let's see if there's something I forgot to talk about on the hand-in page. I think I explained all the interesting lines, and I think I explained 45 filters. So I think that's all good. And if you have any comments, questions, post them in the comment section below. Thanks.